In this video, we're going to be focusing on what isotopes are and then how we calculate the atomic mass for atoms. So if we look at oxygen, oxygen has three known stable isotopes, oxygen 16, 17, and 18. So what's the same between them? Well, we can see that they're all oxygen, so they're the same element. But then what's different between them? We can see that they have different mass numbers, 16, 17, and 18. So this is what an isotope is. Isotopes are the same element because they contain the same number of protons. Remember, protons is the identity of the element, but they have different mass numbers, which is due to a different number of neutrons. So remember, neutrons don't affect the identity of the element. So even though you have different neutrons, you can still have the same element as long as the protons are the same. Isotopes, though, are just different variations of the amount of neutrons, which causes those different mass numbers. So just for some examples of how you can see questions about isotopes, for number 1, it's talking about which two notations represent different isotopes of the same element. So right off the bat, you can get rid of 1 and 3 because you have different elements, so they can't be isotopes of each other. The difference between 2 and 4 is the fact that in choice 2, while they're the same element, they have the same mass numbers. So they're the same isotope, not different isotopes. So that leaves you with 4, which are both beryllium, but that they have different mass numbers, so they're going to have different number of neutrons. In number 2, for that question, it's saying you have two atoms that are isotopes of the same element. They must have, choice 3, the same number of protons and a different number of neutrons. So you definitely have to be able to define what an isotope is in questions. And you're going to see that happen in these next few questions as well. Isotopes of an element must have different amounts of mass numbers. Or they could have given you one asking about the number of neutrons. And then 4, you have 3 nuclides of uranium, 233, 235, and 238. They're asking why they're isotopes, because they have the same number of protons and a different number of neutrons. So just basic definitions of isotopes that you clearly have to know and be able to pick out and pair together. Another big piece of understanding isotopes is being able to calculate atomic mass. One big thing is atomic mass is not the same as mass number. Mass number is always a whole number. It's always the protons plus the neutrons. Atomic mass is a weighted average of all the naturally occurring isotopes of an element. So the number of the atomic mass for iron on the periodic table, there isn't actually an atom that has that mass. This is just a weighted average of all the isotopes of iron, and that weighted average part takes into account the abundance of that isotope when compared to the other types of isotopes for that element. And this is something that you're going to have to be able to calculate given data. So first off, just to check in about the definition of atomic mass, this is talking about titanium. It tells you the atomic mass. It says this atomic mass represents, you always want to look for that weighted average, so we can get rid of 3 and 4. And then you always want to make sure it's talking about all of the naturally occurring isotopes. So you'd have choice 2 there. Be on the lookout if they try to give you an answer that has to do with artificially produced isotopes. We don't take those into account, only naturally occurring ones. All right, so let's work through these calculations of how we take a weighted average. The big thing, this is not a normal average. We don't just add them together and divide by how many numbers we have. We have to take into account their percent abundances. So chlorine has 2 naturally occurring isotopes, chlorine 35 and chlorine 37. In the atmosphere, 32.51% of the chlorine is chlorine 37, and 67.49% is chlorine 35, and it asks for this atomic mass, which right when you see that, you have to be thinking about weighted average. So we're going to take the first isotope that they mention in the percent abundance, which is chlorine 37. The percent abundance of chlorine 37 is 32.51. We aren't going to use the mass of 37. We're going to use the mass that they gave that is more precise. How we're going to do this is we're going to take the percent, we're going to divide by 100 to put it into decimal form. So this is where this 0.3251 came from. And I'm going to multiply that by the mass of that particular isotope. So that's where that 36.9659 comes from. So I'm doing the percent put in decimal form times the mass of that isotope. Then I'm going to take the other isotope and take its percent abundance and its more precise mass, and I'm going to multiply those together and add it to the other one. So I'm going to first take the percent, I'm going to put it into decimal form, and then I'm going to take the mass of it and multiply it, and then put these together. This is similar to how like a weighted class grade is put together by the grade book. So everything is going to be all those masses. We're not adding them together and dividing by 2. We're using their percent abundance. When you plug that all into the calculator, you end up with 35.62. That's the weighted average of chlorine, and that's the number that would essentially be put into the periodic table. Always make sure that that's between the lowest number and the highest number. If you see it fall out of that range, you know something went wrong. Another way that you could see this set up is that instead of dividing by 100 and putting them in decimal form, they'll do that step at the end. So if you look, the only difference between the two is that the percent has stayed a percent for the 32 and the 67%, and then we just show divided by 100 at the end, and you'll end up with the same answer there, which you could round to the tenths or hundredths. All right, let's just give you another example. This one gives you 2 isotopes of copper, and it wants you to calculate the atomic mass. One little thing is you have the isotope notation with the mass number versus the atomic mass of that isotope. So just make sure that you're using the more precise masses. So we're going to use a similar setup. I'm going to take the first isotope, its percent abundance, and its atomic mass. I'm going to take specifically the percent divided by 100 to put a decimal form. It would be incorrect to do that with the mass number, so just be aware of that. Then I'm going to take the second isotope, its percent abundance and its mass. I'm going to multiply them together for the second piece of our setup, making sure that I take my percent and divide it by 100. When I plug that all into my calculator, I get 63.55 atomic mass units, which is great because it falls between the lowest and the highest isotope. And again, you could set this up a little bit different without having to put them into decimal form ahead of time, the percentages. You can simply just set it up with the numbers in the data table and make sure at the end you divide by 100. So you can see the only difference again is that my percent is left in percent form right off the table in this case, and then again making sure you divide by 100, and we'll end up with the same answer. So we will in class practice working with isotopes, identifying them, and then we'll spend a whole lot of time working on calculating atomic mass.